Yeah.
Yeah.
Got the personality that's door right there. Haley, you look cute.
Good day. Hope you're all doing well. How are you feeling?
Ready for fall break.
Yes.
I agree. That thumbs up. I lost my train of thought already, so that's a great start. Fall break, yes, that's going to be great. Speaking of fall break, I don't know if I've said this one out loud in here yet. Hello, why are you doing that?
Did you take that pictures?
I did not.
That'd be really cool.
I was awesome. I always wondered.
I would like to. I very much like stars, and I would very much like to go camping in a place where I
Have
can
you
see
used
that.
Rotifer's like microscope or whatever, or telescope?
So,
It's just microscope.
Sorry, y'all. My brain is biology.
I mean, if you rearranged the lenses, you probably could rig it into a telescope. When I was a student here, I was vice president of the physics group of physics students. We had an organization, I think. SPS, that was it. And because I was vice president, I was apparently in charge of organizing the campus astro nights. Because the physics department here has a bunch of donated telescopes. I don't even know who donated them to us, but probably someone who wanted a tax write-off and didn't have any extra money to donate, just had telescopes. Point is, though, the telescopes were pretty nice, and I hauled them out to, I don't even remember what it's called, the big patch of grass near the townhouses, and there's a field.
Oh, yeah, the Indermere fields.
That one, yes. I hauled them out there, set up a bonfire, and just pointed them at neat things, and students came and had chocolate and looked at the stars.
That's cool.
Round two.
Apparently we're getting SPS reorganized, so hopefully something like that might start up again.
Well, they got that anatomy class. Because that
Anatomy
took,
class?
like, the
Astronomy.
sorry, y'all, my brain. It's,
What is astronomy but the anatomy of space?
but he had that astronomy class for, like, for your first year exploration or whatever.
Oh yeah.
And we, like, would go out to his house and, like, it was really cool.
Yeah, I'm glad that we're still doing something like that.
Literally all I do is anatomy.
Lost my train of thought again. So today is October 6th, and this week continues to proceed as normal. Today we're going to look at a few more examples of friction together here in class, namely one or two that will resemble probably the harder homework questions. I have preemptively gone ahead and made the homework due on Friday, just because I didn't see a reason not to give you the extra time. So this week, finishing out friction, we have a lab as normal, and I am hoping to, maybe at the beginning of today, but definitely by Friday, begin talking about Chapter 5 as well, because we need to keep moving through the material, and Chapter 5 is quite literally just the next step of what we've already been doing. Your hand looked a little more vertical. Was that a question or a stretch?
Yeah, so I know some friction stuff on this homework. So is the homework that's about to be due some more friction problems, or is it going to be like some new stuff that we're going over? Do you know?
Oh, currently there's only one. The homework assignment that is due Friday is the one that's been active, Chapter 4.
Oh.
I have not given a new homework assignment yet.
Okay.
So, the Chapter 4 homework, which I gave a preliminary date of the 4th when I first posted it, I have changed that to the 8th. So it's the same homework, still going over. I'm just giving you extra time on that one because break's coming up and why not? I am making it due before break though because I don't want you guys to have to worry about doing anything over break. I don't want to worry about doing anything over break. I need a vacation, so I assume you guys do too. Anything off topic again. This week, proceeding as normal. Today we're going to work on more friction examples, and then today or Friday we're going to begin looking at Chapter 5. Chapter 5 homework will probably go up around then, but it won't be due for some time. Next week, the school doesn't have classes on Monday or Tuesday, so we will not have lecture on Monday, and there will be no lab at all next week. We will still have normal lecture Wednesday and Friday. The week after that, we will have normal lab and normal lectures. The week after that, we'll have normal lecture, and we'll be having our first test during lab time. I'll make sure about a week prior to list everything that will be on the test. And I am in the habit of posting practice questions for students who are interested, as well as an answer key so you can check your work. They're completely optional, but a lot of students like them, so I keep posting them. More on that as we get closer to it. Any questions about the immediate future, or the homework, or anything at all?
Will the test questions be like more similar to like the WebAssign, or kind of what we do in here? Because I feel like the ones in here are a little bit like easier for me to understand sometimes than the WebAssign.
I think, well, in lecture, if I'm up here talking you through it, it's always going to be a little bit easier, because this happened to me, even me as a student. When you're in class and you're surrounded by people going through the same question, and the teacher is stepping you through that question, explaining the logic, you tend to think to yourself, all right, that makes perfect sense, I can do that on my own. Then you, on your own, later boot up the homework, look at something that's slightly different, and you think, I have no idea what's going on. I try to favor questions that work a little more like the in-class ones, because I'm writing these and my own test questions myself based on questions that I think would work well for you guys. And again, since I am a human that is grading them and not WebAssign's bad AI, I'll be asking questions, I'll be asking for answers specifically that you can just write them and I can just interpret them and I can mark them as correct. You don't have to be in some, you don't have to ask for something specific such that the AI can interpret it. And probably the best part is I'll be in the room with you guys while you take it. And I encourage you to ask questions on all assignments, and that includes the test. The weird thing is on a test, I can't really outright tell you if you're getting the answer correct or not. However, when you get correct answers, it does make me happy. And when I'm happy, I smile. So do keep that in mind. When I smile during the test, it's not some nefarious scheme. I'm usually happy to get it right. Yes?
When is the test?
It will take place during this last week of October. We will have it during lab. There won't be a lab assignment. You'll just go to lab and we'll have the test there so that you don't have to rush in, take an hour test in 50 minutes, and then rush to another class. Any other questions about anything?
Could we come to a different lab date on that week? Okay.
You could, yes.
Everyone's going to show up on Friday now, you know that, right?
Not me.
You're still, as normal, you're going to have to ask me first. And also, I fully expect like slightly different numbers or slightly different arranged questions each day of the week. Sorry. It'll still be the same, like, it'll be graded on the same material. I just have to make it slightly different depending on when you show up. Just for, I was about to say legal, but that's not it.
You said we could have a question about the homework?
Yes.
Okay, well I have one. It's like number 2.
2.
It's like one of those where I felt good about it in class and then like I got it wrong.
Okay. I have had some questions about 2. I think the thing that I'm most commonly asked about 2 is the angle. Can I ask if that's the specific part, or if there's some other part to it that you're... Okay. Okay. Well, let me load up a teacher version that isn't specifically calling out any one student. If it's your numbers and it's marked wrong, I don't want anyone to feel bad. And WebAssign logged me out. Delightful. It used to be that it would just ask me to log back in, but now it says, fully logging you out. You're welcome. If I haven't been here for a day. We have done you the service of logging you out. Please give us more money. All right. So, number 2 is force vector addition. It will mechanically behave similarly to the mule question on the last. And here we have 2 different forces, both acting on the same car. Your forces will both be slightly different, but your directions will always be the same. So I'm going to quickly draw a very poor 3-body diagram. This is our car. Can you tell it's the new Hyundai? And 1 vector, 2 vector, nice known angles. I've got 410 newtons for angle vector 1, and
You have them switched.
I did. Oh, thank you. So, we were asked for the resultant vector, the vector sum of these 2 forces. So they're going to need to be broken down and added together. And exactly how that looks will depend on how you want to do it. Now, this starting picture is a good place to begin. You could just draw arrows on top of this, break your vectors down into their components, add the like components together. When I'm doing a question on the board to try to cut down on like legs overlapping with one another, I might redraw this a little bit, because if we were to use this 10 degrees and this 30 degrees, we get a slightly different color. Oh, am I out of markers? I have 2 markers left. I need to raid the supply closet one of these days. We have 2 vectors. They both need to be broken down into their XY components before we can add them together. If we wanted to keep the picture exactly as it is, we can make that the X leg of vector 1. This is the X leg of vector 2. This is the Y leg of vector 1. And then the Y leg of vector 2 would just be drawn right on top of that, which can work. I just find it a little visually confusing if this is what I'm putting on the board for you guys. But this could still work. Me working this in a class setting for the benefit of people who have to interpret my terrible handwriting, I would probably reframe these vectors to be in terms of a slightly different angle. If that's 10 degrees, this would be 80 degrees. If that's 30, then this would be 60. So that might be how I go about it. Either way, as long as you make sure to keep the same hypotenuse in the same place, you can break them down however you want, but you do need to break them down into X components and Y components using trigonometry, and then add them together, vector addition style, to get a nice new combined vector, which you then have to find the magnitude and direction of. It is worth noting that the X pieces do oppose one another, much like with the mule. So you're going to have to remember to make one of them negative. If you don't do that, your answer will be wrong for both magnitude and direction. But once we get here, we have the coordinates of the new addition, the new vector sum, figure out the magnitude and direction of those coordinates in this form. But I'd say there's 2 tricks to this. There's 2 tricks to this one specifically. One is remembering that x1 needs to be negative. The second trick is the way that WebAssign wants the angle of your final answer. Degrees to the right of the forward direction. So what's on screen now is about 8.38 degrees, which to the right of the forward direction would tilt like this. If you were instead, say, adding your vector, like if you got your two new legs here, you drew them like this, which is a completely reasonable thing to do, I probably would, and then found that hypotenuse and found this angle, your answer would be slightly different. Well, it would be the complementary angle of the actual answer. You could still find the right hypotenuse, but this would be like 8.6, 80 point. I can't talk. I also can't do mental math today, but that's normal for me. The inverse of this would be 81.62. And that is correct, it's just not what WebAssign is looking for. So x1 needs to be negative, and your angle needs to be drawn like, your ultimate answer needs to be in terms of this and not this. Does that help whoever asked this originally? Okay. I've also been getting questions about number 7, which I wanted to do an example like that one here in class today. So that's the main example that I have loaded up to show to you guys. Are there any questions other than something like 7?
Number 6.
I forgot which one that was. Hello. All right. 6 is an interesting combined system. Let me check something real quick. Wait, what? Oh, it's just part A.
Do you need our image?
I really don't. I'm checking actually. I'm checking to see if that's worth any points the way this is set up. All right. So, as I mentioned before, WebAssign is really dumb. It doesn't even have an AI, really. There's no intelligence about it. It can't actually interpret images at all. And oftentimes I will either try to manually remove this type of a question or set it to be worth 0 points, because it can't interpret your answer. You just upload literally any picture and it counts it as correct. That said, you should still make a drawing like this because it will help you to set up the rest of the problem. This is what the picture should be, so if you've been working on it or struggling with it, I will leave this on the board for you for now. The physical situation, we have 3 objects connected as such. 2 of them are hanging and connected by strings to a third one. The third, I guess that's the second one actually. So mass 1 connected by a string on a pulley to mass 2, which is connected by a string on a pulley separately to mass 3. Because mass 2 is on the table, there will be friction as it slides. We're told the coefficient of kinetic friction for that, and we are told the masses of every object. The only source of friction present will be mass 2 acting on the table, which is nice. And part A, does ask you to draw a diagram of all of the forces on each of the objects. Again, you're not going to be graded on an actual picture because WebAssign can't do that, but you should create a picture, and I will talk about what every arrow in this means. Each of these masses are labeled, so M1 is the first hanging mass, tension is going to pull it upwards, gravity is going to pull it downwards, and this isn't a force, but WebAssign has further labeled that this mass is going to accelerate downwards. So we kind of know that the net force on this object should point down and it will accelerate down. Mass 2 is the one with the most forces acting on it because it's tied to 2 ropes and it's sitting on a table with friction. So we have tension in rope 1 pulling left, tension in rope 2 pulling right, normal force from the table pushing up, gravity pulling down, and the force of friction from the table trying to slow it down. That's a total of 5 forces. And we know, well, I am going to tell you, because it makes life easier, that since mass 1 is bigger than mass 2, that this whole system is going to accelerate in such a way that mass 1 falls down, mass 2 is going to slide left across the table, and mass 3 is going to rise. So that one's free for me, just to assuage any confusion about what direction anything is going to move in. And furthermore, we are told the acceleration of this object will point to the left. And then mass 3 is very similar to mass 1, because they are both simply hanging in the air. But this one is going to rise instead of fall because of the direction everything else is moving. So those are all of the forces present. None of them are solved for yet, but having this picture will help you solve for everything. So please go ahead and make note of this if you haven't already. Part B is where the math begins. And this one gets tricky in that you were asked for the acceleration of every single object and what direction it is going to begin accelerating in. And I don't have my work for this one, and it's been a second since I went through it. I'm assuming we're going to reach a situation of similar to 2 equations, 2 unknowns, although it might be 3 equations, 3 unknowns. But what's going to happen is all 3 of these objects are tied together. There is 2 ropes, so there's going to be 2 different forces of tension. And they all have different types of forces acting on each of them. But because they are physically tied together and moving together, they are all going to have the same number for their acceleration. So as long as you find the one acceleration, that's the numerical answer for every part of this question. You do still have to manually decide what direction everything is moving in, so do make note of that. But all you need is the one acceleration. Now to find that, let's see if we can set something up quickly. You're going to need to look at the sum of the forces acting on each object. So sum of the forces on mass 1, sum of the forces on mass 2, sum of the forces on mass 3. We'll just look at the axes in which everything is accelerating. So we'll ignore the vertical axis on mass 2 for now, because it's not accelerating in the vertical axis. The vertical forces acting on mass 1, I will further specify forces on mass 1 in the vertical axis. We just have tension up and gravity down. So tension pulling it up, its own weight pulling it down, and net force has to add up to the mass of that object times its acceleration. So these are the 2 forces added together. This is the resultant mass and acceleration. Object 3, just skip ahead a little bit, is very similar. It has tension 1 pulling it up and its own weight pulling it down, and its variables should add up to its mass times the same resulting acceleration. Mass 2 is a little trickier because it has more forces acting on it. It has the 2 tensions, so tension 1 plus tension 2, and it also has friction working against the net move. It has friction trying to slow it down, so force of friction, and that's going to equal m2 times the same acceleration. Now, the trick to proceed from here. We have approached a situation of 3 equations and 3 unknowns. The 3 unknowns are acceleration and the 2 tensions. We don't have numbers for those yet, but those are the things that we're going to eventually want numbers for. We do know each individual mass. We know -9.8. wherever that's relevant. And we have enough information to figure out the force of friction on mass 2. We know the coefficient of friction, we know its weight, so we can figure out normal force. You can find a number for this using force of friction equals normal force times mu. The thing that you guys are going to have to do, and you have again until midnight on Friday, so we can revisit this on Friday if we need to, midnight on Friday, to use these three equations to solve for A, T1, and T2. And it's the same A in all of them, thankfully. That makes life easier. To find A, which is the first thing you're asked for, I recommend taking Formula 1 and Formula 3 and solving them for T1 and T2, and then plugging those into Formula 2. That will cancel out T1 and T2 and just leave you with A as the only unknown. Then solve it for A. That will be the answer for the three A's in part B. There is a trick though, and it's the direction of everything here. Because for object 1, tension pulls up, weight pulls down, and acceleration will point down. For object 2, T1 points negative x, T2 points positive x, friction points positive x, but the acceleration will still be negative x. For object 3, T2 pulls up, weight pulls down, and A will point up. So when plugging numbers into this, their signs will need to reflect all of that. How's that sound? Okay. What time are we looking at? It is now 10. I'm going to leave this one here for you guys for right now, because I definitely want to go through a specific example to help set up number 7 as well. I've made the homework due Friday at midnight, so be working on it. Let me know what roadblocks you encounter. We can continue looking at this specific one and doing some algebra for it Friday if we need to. So this one, well, I'm a physicist and a mathematician, so I don't think the algebra behind this is super complex, but I'm paid to do this. You have a different perspective. So let me know what roadblocks you encounter there, and I will gladly assist with them. We'll take a quick pause, because I've been talking for a while. And then we're going to look at a friction and pulley example, kind of similar to this one, kind of similar to number 7, just to help get those set up for you guys. Is my screen still on?
Yes.
Great, thank you.
think he does though. Like, I don't know why he would let one class get ahead of the other. But I could also see him not canceling.
I know, me too, I don't know.
Okay. Anyone need anything before we resume? So what's currently on screen is a simpler version of number 6 and is similar to number 7. We have only now 2 masses connected by 1 rope. We know the weight of each of these masses. We actually don't have to calculate weight for mass. We actually know what the weight is. It's just given to us. And we are told the coefficient of static and kinetic friction between this specific block and the table that it is situated on. So let's actually we need to label which one is which. That's called UM1 and UM2. We have our picture. Let's list the variables that we know and don't know. We've got, let's call it force of gravity 1 is 100 newtons. Force of gravity 2 is 50 newtons. Those will point down. I guess we can go ahead and make them negative if we want to, just to show that it's going down because it is gravity. We know the coefficients of static and kinetic friction. And that is all the question outright tells us. We do know some things that we will be looking for. That this system is going to begin moving and accelerating. And we know that there is some unknown amount of tension in the rope. There will also be some currently unknown amount of friction in this system as mass 1 slides across the table. So, first question, just a concept one. Assuming this system is going to begin moving, assuming you set it up, you let it go, and it starts sliding, what type of friction will be in this particular situation between the 2 types?
Kinetic.
Kinetic. We're in motion, so we are going to only use mu k, and we will ignore mu s. We don't need it if the system's moving.
I have a question.
Yes.
Why are the forces negative?
Gravity points downwards, and it entirely just represents down. Either, if I list them as positive numbers, I'm going to have to probably make them negative in the math anyway, because they point down. And sometimes I get questions if I don't label them as negative before I do that. Sometimes you get questions if I do label them as negative before I do that. So, since they're going to need to end up negative anyway, I'm just trying to remain consistent in that. The main thing here is they point down in the vertical axis. That is what the negative means, and that's what this little y means. Any other questions? Okay. So, first thing we're asked, how fast will this system accelerate? Assuming it is moving, both blocks are going to begin accelerating, and, like we mentioned before, since they're physically tied together, they have to accelerate together at the same rate. So even though there's 2 masses, there's only one A to solve for. This setup will look very much like the one over there for homework number 6, but there's only 2 masses this time, so it'll be the easier starter version of the algebra. I'm going to actually keep the numbers out of it for as long as possible so that it's as similar to the setup over there as possible. So let's look at the forces acting on object 1. Actually, we should draw through by the guy. Well, I'll just put the arrows on the picture. Let us determine what all these forces are for now. Tension's going to pull that way, so label that T. If the system is going to accelerate such that this mass moves to the right and this mass moves down, then friction must point in the opposite direction of that movement. Gravity will point down, normal force points up. We'll do the same thing for object 2. Gravity will pull down, but that's with its own weight. I should label these separately. Force of gravity 1, force of gravity 2. It will also be pulled upwards by the same rope with the same tension. It's one rope, the same tension acts on both sides. But those different tensions are acting in different directions on objects with various other forces acting on them. So the same tension in different directions on different masses can still result in the same acceleration for either mass, and the whole system will still move together as one. So, for object 1, we don't especially care about the vertical axis because we're not accelerating in the vertical axis. So let's look at the X forces on object 1. We've got tension pulling it forwards and friction pulling it backwards. Those two things need to add up to its mass times its acceleration. We actually don't know the mass, so we're going to have to recalculate that by working backwards from its weight. Then some of the forces on object 2. The only forces present on object 2 are in the y-axis, so we will only pay attention to that axis for now. For that object, tension pulls up, its own weight pulls down, and those will add up to its mass times its acceleration. Okay. Questions so far? I really should just get a watch. There's actually something that we should probably do before we start rearranging to make our lives easier later. And I'm actually also going to go back and do it for the setup I gave you for number 6, because the fact that everything's accelerating in a positive or a negative in a different axis, we need to make sure we account for every positive and every negative. So before we start plugging in numbers, looking at the forces on object 1 in the sample question on the board, tension is going to pull in what we normally call the positive x direction, but friction is going to pull in the opposite direction. So this number will need to be negative. I'm going to go ahead and put that minus sign there for now. You don't need to plug in another negative and make it positive. This is the sign it needs to end up with. And the acceleration will thankfully still be in the positive x, so nothing needs to change there. For object 2, tension pulls up, which is also still positive, but gravity points down, so that will also need to be a negative number. This needs to be minus the weight, so it is subtraction. If you don't plug another negative into this, and then it becomes positive. And then it accelerates down. So its mass times A will also need to be negative. But once we account for those signs, we can start plugging in the numbers we know and start trying to solve for A. So go ahead and do the same thing over here. Let's see, do I still have the question up? Yes. Okay. Mass 1 is going to fall down. Tension pulls up. Weight pulls down. It falls down. Object 2. Tension 1 pulls in the negative direction. Tension 2 pulls in the positive direction. Friction will pull in the positive direction, but it's still going to accelerate in the negative direction. Object 3, tension 2 pulls up, weight pulls down, but it accelerates upwards, so that's still positive. We will continue to revisit this one on Friday. You'll be working on it though. All right, see if we can wrap this one up quickly because the algebra here will be very similar. Oh, I should put the question back. What's wrong? Okay, we are asked for the acceleration. We need to find A. Now we have two equations and two unknowns. The two unknowns in each are t and then the same A. So we need to solve one of them for t and plug that back into the other one. So, doesn't really matter which one we do. Let's just start from the top this time. So tension minus the force of friction will be mass times acceleration. Tension minus friction is normal force times mu. Normal force will be 1,000. We're going to use mu k. So the normal force on object 1 will be equal and opposite its own weight. Multiply that by coefficient of kinetic friction. And that will be equal to its mass times the acceleration we're after. Its mass would be its weight divided by 9.8. So I'm just going to leave that as a fraction for now. And if we solve for t, we will get 100 over 9.8 times a, which should be something like a little more than 10, right? I'm second guessing myself. Bring this term over the other side, so that would be plus 32. And then take that, plug it in here instead of t. I'll draw a dividing line. So instead of t, we will now have 100 over 9.8 times a plus 32 minus the weight of object 2, which was 50, equals, and this is going to be negative because we know that mass 2 accelerates down, its mass, which would be its weight, 50 divided by 9.8, times the same a. Now we just want to get all the terms with an a on the same side. So 100 over 9.8 times a. We'll bring this whole term over to the left. That'll be now positive 50 over 9.8 times a. We're going to bring these two terms, the 30 and the negative 50, over to the other side because they don't have a's in them. And that would end up being positive 50 minus 30, or positive 50 minus 32, which would give us a total of positive 18. Now, what comes next should be another line of algebra. I'm just going to use the distributive property to transform what's on the board. Use the distributive property to remove the a's. Now we have a times this, which should become a whole number. We can find just one number for that. And that should be 150 over 9.8, which would be like 16 approximately. Somewhere between 15 and 16. Time.
15.
Thank you. What again?
15.3.
Thank you. Oops. Equals 18. We'll divide both sides by 15.3, and that will tell us our acceleration.
1.77.
Thank you. Over 1.7. All right. And they will both accelerate at the same rate together. We could then take this acceleration, bring it back up here, and find the tension. And again, this will be what you do for 16, just with 3 formulas instead of 2. That is the end of the lecture, and I don't want to hold you. So if you have questions, feel free to email them or stick around. You have a wonderful day. You'll be working on your homework. Let me know what issues you encounter as you do that. And just come to lab, say hi to everyone. Okay.